Okay, so it's time to start the last chapter. And we'll be doing something new, but we're just going to be applying old stuff to it. So hopefully it's not going to be anything kind of surprising to you. So, and we're only going to look at derivatives in this context, an optimization problem. So it's something that you already kind of know. So what do we want to talk about? Functions. So we talked about functions as kind of like some black box. In comes an input and out comes an output. And by this black box, I meant, it could be given to us as a table, it can be given to us as a graph, it can be given to us as a formula, or a description, whatever. It was just a rule that allowed us to turn inputs into outputs. And once we had a function, we figured out things how to talk about its rate of change. And that got us to derivatives. And then we started talking about, well, if we're given a function, let's talk about the total change that happens if that was a rate of change. And that's how we got an integral. So what we want to do for the last chapter is just to expand the idea of what a function can be. So we're just used to it as being one input and one output. And if you think about it for a second, there could be as many inputs as we like and as many outputs as we like. So for example, there can be allowed to be one input and two outputs. So for example, if our input is just a person, think of all the outputs there could be. There could be height, weight, gender, age, lots and lots of things, right? Conversely, there could be lots and lots of inputs. So, for example, you could put in latitude and longitude and ask, what is the temperature? There's lots of situations where you're trying to, so you're doing some sort of sales campaign, and the bottom line is how many pizzas you sell, for example. Think of all the inputs that could go into that. There could be, the number of workers we hire, the amount of money that we spend on advertising. If you think of it, there could be lots and lots of inputs and lots of outputs. Okay, and so that is no big surprise. So we want to be able to do the things that we did for these kind of functions on more general functions. And we're not going to go whole hog here. We're not going to suddenly make it arbitrary. We're just going to look at one particular situation. And that's where we have two inputs. Now, X and Y is our input, and we have one output. So this is the single variable case. This is a multivariable case. So there's only one single variable case. There's lots and lots of multivariable cases because it's all the possible combination you do. But this is kind of like the simplest multivariable case. And we're going to just show that it's totally doable. That the stuff that we learned here can be applied to here. And so that's what we're going to be doing over the last 5 lectures. Only 5 lectures to go, folks. So that's exciting. And so it's easy to come up with a formula with two inputs, like for example, f of x, y equals 1 over y minus x, for instance. Okay, it's a rule. I give you two numbers, you plug it into your calculator, and you give me the answer. Okay, so for example, f of 1, 2 equals 1 over 2 minus 1 equals 1. F of 3, 5 equals 1 over 5 minus 3 equals 1/2. No problems there, right? So we can use the same language that we used before. So there's the idea of a domain. Right? What are the allowable inputs? So what's the domain for this function here? What aren't we allowed to have? They both can't be 1, they both can't be 2, so y can't equal x. Right? If y equals x, then you're dividing by 0, and you can't do that. So anything where y is different from x, you can figure out the function for this. You can talk about the range. Right? There's all allowable outputs. So domain is allowable inputs, range is allowable outputs. For this, you can get any number except 0. Right? There's no combination of y and x that will give this number 0. Right? If you plug in, you can solve it for a positive or a negative number, right? Because a negative number just means that x is bigger than y. So the range is, the real numbers minus 0, for example. So these are the types of games that we played when we had normal, just single variable functions. We can do the same thing with multivariable functions. Okay, so we've got formulas, we can have tables, and we can have graphs. So let's do an example of a table. Let's see if I can. Oops, no, I gotta share it with us. Okay, so here is an example of something given to us as a table. So we own some kind of theater or something, we're doing some kind of presentation, and we're interested in revenue from ticket sales. So we have full price tickets and we have our discount tickets. Okay. And so here we've got two, so you can see why we're just interested in two variables, because it starts to, that's kind of like the biggest we can kind of make our table, right? Because if we have two inputs, then we can have row variables and we can have column variables, and it'll fit onto our page. So remember when we had the single variable case, when we had a table, we just had like a one row and lots of columns to represent our function. So now we allow multiple rows, and so we get a table that kind of looks like this. And you see that after a while it gets to be a lot of work to create these tables, because we do a lot of writing, but whatever. So here And you can see how to use this table, right? So say if we sell 200 full price tickets and 600 discount tickets, then here is our revenue. So we just look up the appropriate row and column and we can read it off the table. Okay. We can also represent this as a formula. And of course, the idea about formulas is that it's a much more compact way of writing information. And that gets to be important when we get kind of like these situations here. And so we see, so if we want to turn this into a formula, what would we do? Well, we do, and this is the general strategy in how you attack these kind of problems, is you try and treat it like this problem. And what you do, that is you keep one variable fixed and you see what happens when you vary x. And then you keep x fixed and you see what happens when you vary y. Right? So what you're doing is, in terms of a table, is you look along rows to see if you can see a pattern, and then you look just down a column to see if you can find a pattern. And then you try and glue that together. And that's not so hard in this case. So what happens, for example, when we vary rows? We go from 75,000 to 110,000. So it goes up by 35,000, up by 35,000, up by 35,000. So we see that each time we go across one in a row, we add 35,000. So that means when we sell 100 more full price tickets, we make $35,000. So that means a full price ticket must cost $350. Then we can do the same thing with columns. And we see that each time we go down one column, one entry, we add 40,000. But that's like the same thing as selling 200 more discount tickets. So 40,000 divided by 200 is 200. And so therefore a discount ticket must cost $200. And so we can do this as 350x plus 200y. So this is a perfectly good formula. And then we can use this then to say, well, what happens if we sell 150 full price tickets and 250 discount tickets? We can just plug those numbers into our calculator and get an answer. In general, it's not going to be so clear cut, because maybe, there are interactions and things change. Maybe it's not always going to be one price, in which case you've got to do some kind of interpolation. But that's just, we've done kind of interpolation before, right? Remember when we've had a row, a single row like that, and we've wanted to figure out what something is, say, at 125, well, that's a quarter of the way from this to this. And so we take the difference, we multiply it by a quarter, and that's what we get. So we can do interpolation, but this one is so easy that we can actually just write down a formula. Now, the way that we graphically represent functions, we'll talk about tomorrow, because there are some special techniques that just come from the fact that you're dealing with the graph is something three-dimensional, right? So we have to think carefully how we're going to represent that. So we'll talk about that tomorrow. So here's an example, okay? So we're renting cars. and we charge by the day and per mile. My piece of chalk. Oh, there it is. Okay, so a car rental company charges $40 a day and 15 cents a mile for its car. Okay, so we want to come up with a function for the cost, and it's going to be a function of two variables: the number of days that you take the car for and the number of miles that are driven. How do we put in the number of days? So if we go for D days, how much money is that going to cost us? $40 per day, so it's going to be 40D. Then there's a charge for mileage. So what's the charge for mileage going to be? Exactly. So one little trick that you've got to avoid, right? You've got to make sure that all the units are consistent. So that's always something you always got to watch out. You always got to give units. You've always got to make sure that your units are consistent. So it says 15 cents, but you've got to turn it into dollars to be able to put it into one thing. And so that's a formula. And so we can ask, well, what's the cost of hiring the car for 5 days and driving 300 miles? Well, it's going to be 40 times 5, that's 0.15 times 300, 200 plus 45 equals 245. And at the end, we've got to make sure that we put the units in. And then interpreted, it is easy. It just means it costs 245 days to hire a car for 5 days. It costs $245 to hire a car for 5 days and drive it 300 miles. Not such a hard thing. So here is the strategy. So here is how you think about things. We know all semester we've been studying one variable functions. So we are kind of a little bit of an expert on one variable functions. We know what their tables look like. We know what their graphs look like. We know what kind of things do we know? We know about increasing and decreasing. We know about concavity. We know about steep and shallow and flat, right? So these are all concepts that we've been playing with all semester. And so we want to bring that knowledge to this. Except this kind of looks a little weird. It looks different from a one variable thing. So what we want to be able to do is to use the strategies we've learned before and learn how to apply them to these scenarios. And so that means the strategy is just vary one variable at a time. So the big trick is, right, that if you fix one variable, a 2-variable function becomes a 1-variable function. And we know how to handle 1-variable functions. So that's how we do it. So, for example, let's examine this function. before we get on to that function. Okay, so what happens if we fix D and allow miles to vary? What kind of function do we get? One variable, but a particular kind of one variable function, one that we know a lot about. Is it a polynomial, or exponential, or periodic? It's just linear, right? So it's linear in M, right? So if you fix D, that becomes like the y-intercept. This becomes linear, and this becomes the slope of the function. So when we fix D and vary M, we're getting a straight line with a positive slope. We know perfectly well what's that like. The same thing if we fix M and we vary D. Again, we get a straight line with a positive slope. So what does this kind of thing look like? Well, this is some kind of plane, right? Where when we fix one, it's kind of like taking a cut and we get a straight line. When we do a horizontal cut, we get a straight line as well. Okay, so let's have a look at this guy here. So this is something we've been interested in. It's what happens when we put drug into the bloodstream. And so maybe the concentration of the drug in the blood is a function of two variables, right? X, the amount of drug that is injected into the bloodstream, and T, the amount of time. Because you know, when we get the injection, we get kind of like this peak as the drug diffuses through the body and it's picked up. And then over time, we get this kind of decay as the body collects the drug in the liver and the kidneys or whatever and gets rid of it, and the drug kind of breaks down. Okay. So here is a model. So a model is just a formula that tells us what we expect the concentration to be. Okay, it looks kind of complicated when it's a thing of two functions, two variables. So what we're going to do is look at it by the strategy of fixing one variable. So if you can think about it, what does that mean in this situation? What does it mean to fix one variable and let the other vary? So for example, what does f of 4,2 represent? 4t, right? So that means we give a dose of 4 milligrams to our patient. And then what happens to the patient over time? And so then the concentration is going to equal X is 4, T varies. So it's T E to the minus T times 5 minus 4 is 1. So this is what that function looks like. We did this in class, right? This is the surge function. So we know what it looks like. If we look at fx1, what does that mean? That means we're varying the injection, how much drug is given, and we're looking at how much drug is there in an hour's time for various different initial doses. And we have a formula for that, where we set t equal to 1, and we let x vary. So t equals 1 minus. We get a different, so here we get a surge function. What kind of function is this? Just an exponential function, isn't it? It's an exponential. The growth or decay? Decay, right? Because well, no, it's not actually, because if we do e, distribute out the minus sign, we get x minus 5. So it's actually an exponential growth. Right? As they start injecting more and more drugs into you, the amount increases. So, for example, here is the function 4t, right? So this is just a one variable situation. It shows the concentration of the blood resulting from the 4 milligram injection. And we see what happens, right? It's this. We see B is 1. So that means the peak is reached at 1 hour. It goes up 1 hour and then sort of decays away. So that's what's happened. So this function shows the concentration of blood at a fixed time, 1 hour after the injection, as a function of how much is injected. Right, so if 4 milligrams are injected, then we've got e to the minus 1, which is around 0.37. We've got around 0.37 milligrams per liter in the blood. Okay. And so we kind of think about what is happening with this function then. In one direction, we've got a surge function, and in the other direction, we've got exponential. And it's kind of like you can then kind of, if you think of it, you get slice, 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 slice. In one direction, you're getting a whole bunch of surge functions as we go on here. And as we're going in the other direction, we're getting exponential growth. So just like we looked at this table and we looked at rows and we looked at rows and we looked at columns. With these things, we're really looking at just rows and columns, right? We're just looking in one direction. We're seeing a whole bunch of surge functions. And then when we perpendicular to it, we see it kind of rising exponentially. And so you can actually glue those together to get like a three-dimensional picture of what's happening. So you can kind of think of it as kind of like a landscape, which is kind of a little bit, it's like that you're on. So in one direction, this is what you've got like a mountain, and then in the other direction, that mountain sort of grows and grows and grows. So some people, this is not really a math problem. This is like a 3D visualization problem. So some people are really good at visualizing what happens in 3D. So usually those people are artists and stuff like this, but this is kind of math. So some people are good at this, at some aren't. And so one thing you can do then is then one way to represent it graphically, it's not the main way, we'll talk about that tomorrow, but what you can do is just put a whole bunch of these different graphs together on the same axes, right? So you can, so in this case here, we can put in C of x1. So this is x, this is the concentration, and then you can put in, you know, another thing. You can put in C of x2, for instance. You can just put in a whole bunch of them just to kind of show what's happening. Remember, what's the most basic thing we can ask about a function is whether it's increasing or decreasing. But if you've got two inputs, you don't have a single answer. In this case here, it's an increasing function of x and an increasing function of y. But you're allowed to have an increased function of x and a decreasing function of y. Right? So when you talk about describing the variable, describing the function, you've got to take each variable at a time. So here's another situation. So you're at an airport and fog comes in. So what they sometimes do at airports is they try and heat the air to try and remove the fog so that they can take off. Okay. Or, you know, they might say, well, the sun's coming out, the sun's going to heat up. It'd be nice to know for us to be able to predict when the fog is going to clear. Okay, so how much heat is needed to clear the fog depends upon two things. One is how cold it is, the temperature. And the other is how wet the fog is, how thick the fog is, right? So temperature, we can just measure in degrees. Wetness, we measure in grams per cubic meter. So how much water is actually in the air. And so, yeah, grams per cubic meter. Okay, so here is a whole bunch of graphs, a whole bunch of side sections where we're allowing temperature to vary, but we're fixing how wet the fog is. So this is the curve of this wetness, this is the curve of this wetness, this is the curve of this wetness, this is the curve of this wetness. Okay. Basic question. Is this an increasing or decreasing function with regards to temperature? So as the temperature gets warmer, do you need more heat or less heat to clear the airport? Less heat. So therefore, it's decreasing in T. And we can see that. You can all see that from the table because we see that's a decreasing function, right? What about in wetness? Is it increasing or decreasing? It's increasing, and that is because these lines lie above each other. Okay, so when you double the wetness from 0.1 to 0.2, you need more calories to clear the fog. And then when you go from 0.2 to 0.3, you need more calories. From 0.3 to 0.4, you need more calories. So it's increasing in W. Okay. That is kind of like the most basic question you can ask about a function, whether it's increasing or decreasing. Okay. So what else can we do? So we can figure out what h of 20.3 is and interpret that. Well, t equals 20 is this vertical line here. 0.3, oh, luckily we had a graph here. So we can look at 0.3 at 20. So we're interested in this point here. And what value is that? Yeah, let's say 260. So h of 20.3 is 260, and we look at the units, it's calories per cubic meter. What does this mean? It means that when the temperature is 20 degrees and the fog has a wetness of 0.3 grams per cubic meter, we need to heat the air by 260 calories per cubic meter to clear the airport. Okay. That is what that statement is. Okay. So again, the reason why we use formulas is because it packs a lot of information into a very succinct statement. Okay. We could also turn this into a table. So maybe we find that graph a bit off-putting. We can turn it into a table. We're not going to do all of it, but let's just, what do we need? We need that's column variables. And that's temperature, and wetness is going to be our row variables, and it's going to be 0.01. You can see what a lot of work this is, right? Because it's multiplicative, right? It's 5 times 4, so we've got to figure out 20 things. But like, for instance, we figured out 20.3 was 260. And we just do that for all these points here. And we can fill in the table. So for example, 0.4 looks like it's around 580 maybe, etc. And then the lowest was 40.1, which looked around 70 to me. And you can just fill out all the data as well. And sometimes that's good because tables kind of depends on how your mind works, which one gives you more information about kind of what is happening. Okay. So here's a function in a table. So is this basic question, increasing x, increasing of y, or decreasing So have a look at that. B. So you say that it's increasing in terms of X. X is the row variable. So what happens as we go down a column? As we go down a column, we see that we're increasing. That's X. So it's an increasing function of X. What happens when we look across columns? We see that when we go along a row, that it's decreasing. Decreasing everywhere. That's the Y variable, so it's a decreasing function of Y. B is indeed correct. Okay? Okay, so this is now a thought problem. So you get a loan to buy a car, and we're thinking about the total amount that you pay out over time. You're going to think of that as a function of the down payment you put in and the interest rate. This is the total money that you pay over time. So we're not worried about present value or future value. We're just talking about the face value of the cash that you hand over. Okay. If we hold the interest rate fixed, is this going to be an increasing or decreasing function of P? Decreasing. So what you're saying is that the more money you put down at the beginning, the less money you're going to pay over time. Do you stand by that? Yes. Everyone agree that, right? Because you're paying interest on the money that you're outstanding. If you put more money up front, there's less money for the interest rate to work on. So you're going to end up paying back less. So yes, this is a decreasing function of P. Let's go the other way. Now we fix our down payment. And now we say the interest rate is allowed to vary. Is this going to be an increasing or decreasing function of R? Elijah, what do you think? Interest rate goes up. Are you going to pay back more money or less money? More. More. It's increasing function. Exactly. Here's another one to think about. Okay, so we've got some birds on an island. And the number is going to depend upon the number of hawks and the number of insects. Now, you've got to think for a while how that's going to depend, right? So obviously what happens is the hawks eat the songbirds and the songbirds eat insects. The chain of life, right? So here are, so there's some possible interactions between the populations. So there's, so we let one population increase while the other remains this constant. What's going to be the effect on the songbirds? So as the number of hawks increases, what do you expect that to happen to, what's going to happen to the songbirds?
decreases.
Why?
Is there predators that are coming?
Yeah, they're going to eat more birds. Okay, so we definitely think 2 is true. What's going to happen about the insects? What happens as the insects increase? Is that going to have any effect on the birds? Why? Because it's what they eat, right? So the more food they have to eat, the more of it. So we definitely think 3 is. So we think 2 and 3. So we're going to go with C. Yeah. Okay. Here's one problem that we haven't seen before, but using the logic from before, we can handle that. We have a function, and we know that f of 0, 0 is 50. And we want to estimate f of 2, 5. And we know that f goes up by 3 when x goes up by 1. And f goes, what happens? Goes down by 2 when y goes up by 1. So what do you think f of 2, 5 is going to be? What do we expect f of 2, 0 to be? This is the kind of problem that we looked at, right? We talked about if we have a quantity and we have a derivative, a rate of change, then we can approximate, right? So if at 0, the derivative is 3, what is going to be the value at, what is going to be the increase over 2 units? It's going to go up to 56, right? It's going to go up 50 plus 6. And this is the change that's due to x. Well, what about f0, 5? If we just think of it as a function of y, what's going to happen? It's going to be 50. And how much is it going to change by? 10. We expect it to go by 10. So this is just doing linear approximation, like how we knew we did it with single variables. We just take our delta x, our change, and we multiply it by the derivative to get the change. Well, if this is the change that's going to be due to x, and this is the due that changed to y, what change do we expect if we do both of them at the same time? -4, exactly. And so we expect the answer to be 46. Again, using the strategy of taking one variable at a time. Okay, that's enough for today. We will continue this tomorrow. Okay, so this was the new thing. Okay, so hopefully I'll give you some homework for it. Is anyone doing anything for the student research conference next week? Okay. So no one needs any special thing for that.
So tomorrow the office hours would go like directly after class, I'm pretty sure.
Yes,
Is that right? If my group just talks to you after class and goes
Sure.
over our project?
sure. That's,
Okay.
that'll work good.
Thank you.
So you're just going to,
I mean, I don't think anybody uses this room after us.
right,
Maybe
okay.
We just quickly go over a couple of things at the end.
Okay, that sounds good.
Thank you.